Okay, so this tutorial will be using a game engine called Unity 3D. I want you to go to their site, download their engine, and open a new project. We'll go from there. Now that we're in Unity, what I want you to do is go up to the top left Create tab and create an empty game object. Then after that, I want you to go down to the Assets folder and create a new C# script. After the script is created, open the script by double-clicking. Finally, drag and drop the script onto the game object, and you're ready to go. Okay, so this is the actual core of the tutorial. So here I'm going to actually explain to you what we're going to be going through here. So I'll just jump into it right now. So basically, by section, what we're going to do is first things first is we're going to cover what the heck this matrix is. It's a very important question. Basically, what this matrix is a translation of what I was showing you in the theory. So you can actually use it for an algorithm. But we'll go more in detail about that soon. Then I'm going to go over all of these references, like why you need these specific things. There's a variety of ways to do Dijkstra's algorithm, but this is the way I found was useful. Then we're going to actually jump into the actual algorithm function, where we're going to go through step 0's implementation, step 1 and 2's implementation, and returning the shortest path, as well as some simplifications you can do to step 1 and the actual method of returning the shortest path. So yeah, first things first though, we start off with this matrix. The matrix, as I said before, is actually a direct representation of this graph that we've seen a ton of times in previous tutorial. So how we get from here, this graph, to a matrix is first we number off all of the possible nodes in the graph. So all the nodes in the graph. And we map out all the relations of every single node. So what that means is that for all of these nodes, we'll go one by one, where we'll go first at the 0 point. So for 0, 0's relationship with itself is 0. There's no, it's just itself. So it gets a 0. And 0's relationship with 1 is 2 because there's a connection between it. And it gets a 2 because of that, because the weight goes here. The next thing that will happen is that it will check the following one, 0's and 2's relationship. That will be a 1. And then it goes to 3, 0 and 3's relationship. Now, since there's no direct connection, like between 0 and 1, there was a line with a weight, and 0 and 2, there was a connector line or an edge with a weight, but 0 and 3 don't have an edge between each other. So that just becomes a 0. And it's the same for all the rest of them. So for 4, there's no edge, 0, and for 5, there's no edge, 0. And you'll go down and do that for every single one. So for 1 has a relationship with 0 of 2. 1 has a relationship with itself of 0 because it's itself. And then 1 has a relationship, doesn't have a relationship with 2. There's no line, connector line, so that will be 0. 1 has a relationship with 3 of 1 because there's a connector line, the weight is 1. And then 1 has no other connector lines, so 0 and 0. And you'll do this all the way down. And what you might already start to see is that that's the same translation as the graph I showed here. 0, 2, 1, 0, 0, 0. 2, 0, 0, 1, 0, 0. If you look back, 0, 2, 1, 0, 0, 0. 2, 0, 0, 1, 0, 0. I literally translated this graph and did a direct representation here. So that is how you go from a graph like this to a matrix and end up with something like this. Okay, so for the variables that will run Dijkstra's algorithm, you are going to need a variety of things to be able to get this algorithm to work properly. First thing is just some kind of data holder for all of the graph information, which is already put in as a 2D int array. So as you can see, this is already implemented because I didn't want to have to go through and type everyone, just have you wait there. So if you want to pause the video and take it down, you can. So that's the first thing you need, some kind of data holder for the graph you want to traverse. The next thing you're going to need is some kind of node count. So how many nodes are present in the graph? And that can be represented like this. So since this node count will be used in multiple functions, I just made it a global function, a global variable, sorry. That's an int, which will hold all the nodes in the function. The second thing you're going to need is some kind of thing to hold the shortest path. So you're going to need something at the end of the day when you've done all the calculations that holds what you really want, the shortest path from one node to another. And I represent that like this. So this shortest path list is static because I'm going from the angle of, rather than having a bunch of instances of this algorithm, you have one algorithm which you just a bunch of things run through. It might not even be the best way to do it, but it's the way I usually do it, and so I'm doing it like how I prefer. And all this at the end here is just an instantiation, so it's like instancing it, making it like a list, because if I just tried to add without doing this, I believe it would cause an error. Then the final thing, and not to be forgotten because it's very important, is the node's attributes. Now, a lot of tutorials do these things separately, but I decide to put it in one struct so that to contain it and make it easy to understand. So I'll just write that struct now. Not a struct. Okay, so the node, as I've written, has three major attributes. Is the node permanent? How far is it from the source? And what is its parent? As you can see, if you remember from our previous video, that is the three core things that you traditionally get from a node, or any given node during the Dijkstra's algorithm calculation. Is it permanent? How far is it from the source? And what's its parent? With these three attributes to the node, you can basically solve and get a shortest path out. And that's it for basically the variables of Dijkstra's algorithm. And with these, you should be able to, or we will, create an effective and useful Dijkstra's algorithm. Okay, so we're going to finally get started on Dijkstra's algorithm, the actual function. And as you can see right off the bat with the functions, what it's taking in for parameters, you can see it's taking in the graph as data. It's taking in a node source and a node destination. So the start of your algorithm and the finish of your algorithm. So you can already see that this is going to be a very dynamic function in comparison to what you traditionally get with a lot of tutorials, and they just do a general search. So we're going to need to satisfy everything that the parameter is taking in and actually get that start to finish functionality. So to start off, before we do get into any of that heavy lifting, we first need to set up a lot of our variables. First one we're going to set up is the node count. To get the actual node count of this graph, we can actually go to the graph itself and get its length. Now, it'll say dimension here, but you can take either one because it's a square. So 0 or 1 should work. The next thing you're going to do is you're going to go and set up at least a list, or an array, sorry, called node set. And that array will contain every node in the entire graph. So it will represent each node and will hold the attributes, since it's a struct, it will hold each attribute of every node. So this will allow you to keep all the nodes' attributes in one place when evaluating. Finally, we'll actually get to step 0. Finally, a step of Dijkstra's algorithm after all this time. And the first step, we will do a for loop. And it will go for every single node in the graph. And it will go one by one through every single node. And what we're doing here is we're setting, for every node, the distance from source to be basically infinity. We will actually call it int.max value, but what it essentially is doing is setting it to infinity. And we're going to set the permanence to false. Now that's all the nodes that aren't the source, but the source is different if you remember from the theory. The source needs to have a distance from the source of 0, and it also needs another interesting element which I'm going to show you in a second. So first things first, the node set source distance from the source will be 0. Also, its permanence, actually we don't have to do that because it was already set to permanent here because it ran through every single node. But the other thing we need to do to the source is set the parent of the source to -1. The reason we're doing that will make more sense later, but understand that basically we're going to run a process where it will backtrack from the final node to this node. And having it as -1, the source blocks -1, source node's parent as -1 will tell that function it's time to stop. So yeah, that's step 0 for the function. In the next section, I'm going to go over step 1 and 2, the core of Dijkstra's algorithm. So now step 0 is done. So what that means, we can move on to step 1 and 2, like the core of Dijkstra's algorithm. So for that, the first thing we're going to do is we're going to create a for loop. And this for loop will go the length of every single node -1. And you don't have to do this. It's just like a little efficiency, because when you evaluate every node, it doesn't matter. You don't have to evaluate the last node in the set, because the last node in the set is always, even in the worst case, is going to be your destination. So once the calculation has got that far, you don't really care. It's kind of one of those things where at that point it's finished. However, this could also cause a problem where in the worst case it could not evaluate and then you don't get your shortest path back, which would also be an issue. So it's probably just safer to use a standard node count without any -1. Just even though it gets a slight edge of efficiency, it could also fail, which is just not worth it. Count ++, so it's going up individually. And then we begin what is basically step 1. Now, the first thing I'm going to do is have my phone go off and call a function called minimum distance. And minimum distance is going to take node set. Now, I'll describe no set down here because it's the main element of step 1. What node set is going to do is exactly what step 1 does. It's going to take in the entire set of nodes. It's going to check for the node which has the least value assigned to it, like the lowest source distance that isn't already permanent. So if we go through the code for that, we see the first thing it does is it makes a min int, which will be like the minimum value, and sets it to the highest number it could possibly be. And it also sets a minimum index, which is going to equal to -1 as like a warning if something has gone wrong. Because if you get a -1 back from this, then something's gone horribly wrong. Then it's going to run a for loop, which will go through every single node. And in that for loop, there'll be an if statement, which basically does for every node, if it's not permanent, so permanent equals false, so it's not permanent, and the node set at that same node, its distance from source is less than the minimum distance, then minimum will be set to that specific node distance. So basically what you're eventually going to do is you're going to go through everyone and say who has the lowest distance from source. And every time you find the lowest distance from source, you'll update the min index, which is like which node is it that has the lowest distance from source. And when you're all done this for loop, you should have the node with the lowest distance from source, and you'll return that back to the main function. So that's what it'll get back. You pass in the node set into min distance, and it gives you out, okay, this is the node with the lowest distance from to source. That's basically step 1 done there. Then what will happen is that you will go and set that node that you just picked as permanent. You just completely close the loop because it's already been evaluated. You don't want to evaluate it twice, just as I said before. And that's basically the end of step 1. You can say this was step 1 up here. And now we go into step 2. Step 2, we're going to evaluate every node in relation to one specific one. So we've found this minimum node now, this node with the lowest distance from source. And now what we're going to do is compare that node to every other node to see if any of its related partners, any of the nodes beside it which have edges to it, can have their values changed. So that, for example, in that classic example where you have the 0, infinity, infinity, and it becomes, say the weights to those two are 2 and 1 respectively, the 0 will change, that node will change the infinity at the top to 2 because the weight between them is 2, and the bottom to 1 because the weight is 1. And then the algorithm can keep evaluating. So to do that, it's a fairly long and annoying if statement. it starts off with node set at this specific node we're evaluating in comparison to the lowest distance from source node. And we check if it's permanent. Because if it's not permanent, we can go ahead. But if it is permanent, we don't care. And then we go to the graph, which has all the data relations. So it has all the weights. In comparison, it says, okay, with U's data relations, is V in that data relation not 0? So is it something? Is there actually a connector line between U and this specific V, this specific node V? And if that's the case, then we say node set at U distance from source not equal to int dot maximum value, which is basically saying like, and it's not like the U we picked is not max value, which means something went horribly wrong in the algorithm. So something didn't fail on us. And of course, if that's the case, see, there's a lot of checks here. We can finally go to the evaluation where it's if node set U dot distance from source plus graph at U V is less than node set at V dot distance from source, then we can finally evaluate what's inside this if statement. And it is, as you can see here, it's literally saying the distance from source of the U block, the one that has the lowest distance from source, plus whatever the weight of the connector line is, or the edges, to this new other node V. If that's less than what the current node set, like the current V's distance from sources, then that will replace it. And that's what I'm about to write. So node set at V dot distance from source is equal to node set U dot distance from source plus graph U V. And of course, so we can get this whole thing out at the end, we have to keep setting parents. How do we do that? Well, V at this point, its parent has to be U, because we know there's a connector line. We know that going through this process iteratively, it's the one that won out first, so it means that U evaluated before V. So we can guarantee that V's parent is U. And that is basically steps 1 and 2 implemented. That's what it looks like. And with that, we move on to finally returning the shortest path, which will be the next portion. Alright, so after all this work, we're finally at the end. This is the last major piece of code, getting the actual shortest path out. Now to do this, we're going to need a little bit of recursion, or at least that's how I do it. So we're going to start running a function, which is going to be static because everything's been static as far as functions go. They have to bleed into each other. Void, so it's not going to return anything, shortest path. And the shortest path will take in the node set. And it will take in the destination. You'll see why very shortly. So remember when I mentioned how the parent of the source has to be -1? Well, because we made the parent of the source -1, we can do something interesting like this, which is just we set the node set. We say if the specific destination or the specific node we have during this portion of the recursion, its parent is not equal to -1, then we add it to the shortest path, and we recurse. So shortest path, node set at destination dot parent. So that will basically continue the recursion. Now what we've done here is that it basically, every time it runs itself, the shortest path algorithm, what it will do is it will first check if this specific node's parent is -1, so the starting source node's parent. And since it's starting from the end, the first, say it's a 3 long chain, the first one obviously won't, so it'll add the end node, the destination node, that will recurse to the end node's parent, which will be like a middle node. And it will check this, and it also won't be -1. It'll be added, and its shortest path, and then it will recurse again. And it finally will hit the source node, and the source node will have a parent. So this won't run again. And when that doesn't run again, we have an else statement now, which all it does is just adds the final source node to the shortest path list. And after we're done that, you can actually put it up here. We just return. And that will return all the way up through all the layers of recursion. And with that, we will have the shortest path. So we simply need to call it now. We call shortest path, node set, and destination. We will get the path up. But if you remember how the recursion works, it goes from end to beginning. So it starts at the end, adding the last node, then the second last node, the third last node, fourth last node, all the way to the source node, the very first node we evaluated. So the entire list will be backwards. However, lists actually have this beautiful thing called reverse. And now our shortest path starts from the beginning and goes all the way to the end. Now, I'm going to just write something very quickly to check if our algorithm evaluates. So I'm just going to say for each int node in shortest path, debug.log node. And next time I'm going to, or next section, I'm just going to run this and go through it. And I probably will also show you a visual example of this as well, running in a game I'm building. Okay, this is going to be the last section of this tutorial. In it, we're basically just going to run the function. So for this to run, we're going to need to put it in the awake. We're going to need to call Dijkstra's algorithm, the Dijkstra function we made, in awake. So to do that, we'll just type Dijkstra, and we'll pass in the graph that we have up there. So this graph data, and then we'll pick a random number for the source and a random number for the destination. And with that, since it's in the awake function and it's already on a game object, when we press play, it will immediately evaluate. And since we have this little for each down here, it will tell us every element of our shortest path. So let's do it. So let me save and press play. And there we are. There's the evaluation. 2, 0, 1, 3, 4, 5. Now, if I can show this on screen right now, that is actually the correct path for this specific graph. And yeah, right there and then you have a full implementation of Dijkstra's algorithm. One little hyper efficiency thing you can do actually, just to make your graph even a little bit more efficient, is you can say if u equals destination, you just break the for loop. What that will do is that if you hit the source block you want, it basically means you already have the path. So you don't need to go any farther. So it saves a bunch of evaluation time. And as I promised, on the screen right now showing should also be in-game footage of a more practical use of this specific algorithm. And with that, I am done. If you have any questions or comments, this is the end of the tutorial. Please put them in the comments section, and I'll be happy to get back to them as soon as possible. All the best.